Excellent. So this morning, I will talk in part about the solid geology interpretation in the Eastern Fold Belt, but I presented a bit on that just recently at the conference in September. So I wanted to touch on a couple of projects, and including the work that Janelle has mentioned that I've been working on with Janelle and Dom on the seismic interpretation. So the key results that I'll talk about include interpretation of the basement terrains and crustal architecture. I think by the end of this talk, you'll understand just how important I think the extensional fault architecture is. And my understanding of that started with the solid geology interpretation work in the Central Eastern Fold Belt area. Because it fundamentally controlled the structural style during later Eisen shortening. We see a lot of detachment faulting, both in the basement and the cover basins. And between the seismic and the MT data, we're seeing evidence for where some of those major fluid and magma conduits may be, as Janelle talked about. And they're both steep structures and low angle structures. And the implications from this, when you think about thermal anomalies, you certainly want to be considering the extensional history and in terms of driving the fluid flow. Some of the non-magmatic IOCG deposits, because we certainly see quite an array of IOCG styles. Some of those could be detachment fault related deposits, and Monaco's been flagged as an example by Zapatini in a recent paper. Any of the mineralization associated with the detachment faults may be quite difficult to identify because it was, in general, would be early and then has been metamorphosed, remobilized, overprinted, and with a bit of luck, upgraded. So I'm not going to go into a lot of detail in the mineralization. I'm going to give you that background context. So the detailed solid geology interpretation is highlighted here. It's just between Cloncurry and Cannington, and that really built on earlier work by Mark Hidman to the south and west. And then the regional seismic lines that I interpreted with Janelle and Dom are highlighted there in blue. We integrated the MT data and they did the gravity modeling to test our model on each of those lines. And then there's a few other interesting offshoots that I'll mention as I go through. Starting with Mark Hidman's Timespace Chart, I've just highlighted a few of the features. So the three main super basins in the west, at 1680 to 1670, we have emplacement of the Sabella batholith as part of a major extensional event. In the west, we have a significant period of uplift and erosion. In the east, that's when we have deposition of that middle coarser grain quartz-rich unit of the Soldier's Cap and Curry-Dala groups. Now, that's the main extensional event I'll talk about through this talk, but there's certainly been a long history of extension before and after through the Mount Isa region. Sorry, just trying to get it to advance. There we go. I'll move that window out of the way. This is the results of the detrital zircon study from the present day drainages, essentially between Ernest Henry and down to Cannington and Pegmont. So these authors highlighted this increasing juvenile input that peaks during Soldier's Cap group, Curry-Dala group deposition. That's highlighted in the blue there. And that first peak that you see is at about 1675, and so that's exactly where we expect it to be associated with that main extensional pulse. But there's another peak that when you look at the details, there's a couple of peaks around 1630 and 1625. Now, that's not currently recognized in oak crop associated with these units in this area, but it does coincide with extension in the western succession and overlaps in age with the Tommy Creek block. Now, the authors looked at that and said the populations are too significant, and given the location, it's highly unlikely that they can be related to units from the Tommy Creek block. So they argued that this was further deposition and magmatism associated with the Soldier's Cap group or a later unit on that eastern margin. It may be largely eroded, but it may well still be there in outcrop and we just haven't recognized it. So something to keep in mind. Now, we've had a lot of discussions and at a few of these forums on steep versus low angle structures when we're interpreting the seismic. Now, it's always going to be difficult to image some of those steep structures well in seismic data. And there's a range of issues that will be significant in some areas. But for me, the three key factors in this area relate to the fact that the present day erosion surface for a lot of areas is broadly near the brittle ductile transition. So in the outcrop is dominated by those later steep structures and brittle faults, whereas when we look at the seismic, we're always going to be seeing focused on that ductile part of the crust in terms of ice and orogeny timing. But the other two factors I'm highlighting here relate to structural style. This example shows just a simple normal fault and growth package with just minor erosion and a couple of key features. You can see the antiform dies out at depth, and that's something I observed in the data when I was first looking at doing the solid geology interpretation at the start. There's no associated synform in most cases unless you've got this top layer preserved. And if you have a weak layer, you can end up with very complex internal deformation and much steeper structures. Now, looking at this example from the Alps, we've got a more complex extensional fault system that's been inverted. And you can see here at surface, we have steep faults, steep folds and axial planes, but this is 3 to 4 kilometers below surface. Everything flattens because we have development of detachment faulting in a weak layer. And I think this provides a very good analog for some areas of the Mount Isa inlier. Now, I'm going to jump and very briefly touch on basement terrains. Janelle showed a few examples, but just to give you a quick overview, starting with the map, in the west, we see the Ultrawara, Tennant, and Murphy terrains with east-west boundaries. And this interpretation builds on earlier work with FrogTech and colleagues there. So they had to be assembled before collision of the north-south trending Mount Isa blocks. And looking at the seismic, starting there at the bottom on CF3, we identified two distinct terrains there in the Mount Isa region. The trapezoidal elongate Pitta block, which is quite thick and competent at depth, which is overlain by a very thick tabular block we've named Central Isa. So there is a shear zone along the contact, and the Central Isa has been thrust over top of the Pitta Ultrawara boundary. And that all happened before emplacement of the Kalkadoon-Leichhardt belt. Now you can see where I've flagged with the red arrow where that Urandangi-Burketown fault zone that forms the boundary comes to surface. And I think reactivation of that structure is controlled deposition or localization of the Leichhardt superbasin in the west. And then after that, Newmel and Abingdon were accreted sometime. There's debate on exactly when that happened. It had to be well before deposition of the Soldiers Cap and Etheridge groups further east, because those units were, that basement was extended when those units were deposited. Now, looking at this in 3D, so highlighting Central Isa and Pitta, you can see we've got the view looking north from CF3 and M6 in the south. That's the outcrop boundary in orange. The Urandangi-Burketown fault zone traced in there. Now, the Gidgee structure forms the eastern boundary, but when you look at where the Gidgee structure projects to surface, labeled GSS, that sits to the east and within the cover basins. It gives us no information on the actual limit and extent of those basement terrains at depth. So the dark gray boundary here, Gidgee structure at depth, GSD, is highlighted because that tells us the information we need to understand about those basement terrains. And I've just put a couple of yellow circles to highlight that position in the 3D image. The Numal block, we see three distinct, or the Numal terrain on the 07 IG1 line, we see three distinct blocks, which we've imaginatively named West, Central, and East. Numal West, we can certainly see on the M4 and 94 lines. Numal Central, just on IG1 and CF1. When we look at these southern lines, CF3, M6, and M5, the Numal crust we see there is dominated by west-dipping seismic reflections and west-dipping fault blocks. And that correlates more directly with the Numal East terrain. So this is something that needs a bit more work, and hopefully Janelle's new survey will help us better understand that, because, and I think the extent of the Numal West block, because it's a competent block, it has had a strong influence on both extension and basin development, as well as later compression. And I think that's a factor in differences that we're seeing in the MT data. So next, we'll just look at the 94 line in a bit more detail, just to look at those detachment faults. Because as Janelle flagged, this goes through oak crop, and we have a lot of mapping and exposure along here, and we know we have a lot of steep structures. But starting in the east here, we see the folded stably detachment that flattens at about 2 seconds two-way time. Then stepping down and west, the overhang detachment, which merges into a detachment fault beneath the Mitakuti culmination at about 4 seconds. There's a detachment structure sitting here beneath the Kalkadoon-Leichhardt belt. And then the May Downs fault is listric and flattens at about 7 seconds, but probably feeds into that detachment structure at about 5 seconds. So the May Downs fault I'd interpret as originally forming part of that Urandanji-Burktown fault zone that carried the central Isa terrain to the west, but it's been, with reactivation and extension, it's linked into that detachment fault. So the steep structures at surface, contrasting with flat or moderately dipping structures in the seismic, makes sense when you can interpret the detachment faults. Now, this is one of the interesting offshoots. With all the evidence for extension, I started wondering, well, what did that basin look like, or what did the crust look like when that basin formed? So I submitted an abstract and then had to come up with a model. So this is my my model at 1620. So the wedge-shaped geometry and thickness of the Mount Isa crust comes directly from the present-day seismic. The Numal crust is more tapered and thinner and dominated by low-angle faults, as we see in the various seismic lines. I've highlighted the high iron tholiites in the bright green. They have a juvenile mantle source, and George Gibson and GA colleagues have suggested that the crust had either breached or was close to rupture when they were emplaced. Now, I'm sure some of you are skeptical about my 10 to 20 kilometer thick basin, but when you look at the present day thickness, which varies from about 9 kilometers to 15 kilometers of those units, and then think about that missing stratigraphy that's younger than what we're normally seeing at 1650, younger than 1650. And the fact that pressure conditions during peak metamorphism at Cannington here on M6 and north towards Cloncurry are at least 4 to 7 kilobars. So we've removed 10 to 20 kilometers of overlying sediment. So that tells us we had quite a thick basin. So once I've gone out on a limb this far, we may as well take another step and think about that main phase of extension at 1675. So we've got Sabella batholith being emplaced in the west, deposition of that middle quartz-rich sandstone, and this is it's the end of the deposition of this unit when we expect the Broken Hill style mineralization. I have no direct constraints on just how thin that crust was, but clearly the geotherm would have been very high. So thinking about exploration for Broken Hill style mineralization, you want to be off on those margins. So in order to better understand the prospectivity of a given region, if we can try and understand the basin structure in the now shortened basin system, we'll have some further insights on where to be looking. The other point I want to make from this is when you look at this basin, so this is 1620, and the Eisen shortening followed very quickly. After this, you can see how that crustal architecture and extensional fault system controlled the later Eisen shortening. So as soon as we start to shorten, we invert the normal faults, but we're very quickly going to have a room problem because we've got such a big, thick basin. Then this results in translation and detachment fault development facilitated by the calc-silicates in the sequence. And eventually the numal crust will be thrust beneath the thicker, more buoyant Mount Isa crust. Now, Janelle has set the scene nicely for the MT data, and I just want to focus on, the benefits of the integration of the seismic and the MT using this M6 line. And you can see some key features here, but I was quite stunned when I first overlaid my final seismic interpretation. And so this is the terrain boundaries and major structures, and suddenly that data set makes a lot more sense. We can see conductive anomalies associated with east moderately dipping structures within the central Isa basement terrain, and in the cover sequences, we can see a more moderate conductive anomaly associated with the top of the numal and the Gidja structure. And then the steep Pilgrim fault and Cloncurry faults clearly have a role in the resistivity structure of the crust through this area as well. The Williams and Maramungi suites have distinct neodymium model ages that can be related to the presence of the numal crust at depth as opposed to the Pitta Pitta and Central Isa terrains. Early work by Mark suggested a source region that was at a maximum of 24 to 30 kilometers depth, which puts us right there at the top of the numal in that area where we're seeing that moderate conductive anomaly. So thinking about the moderately dipping structures and the steep dipping structures, which all seem to have had a role. So the moderately dipping structures were active during extension, and then during the early stages of shortening and through to crustal thickening and peak metamorphism. But you can see here that and this is evident on M6 and CF3, the Gidja structures folded. So that structure started to lock up, it folded, and as the shortening became more oblique and led to transpressional deformation, that's when the steep structures became more dominant. And we'd have an obvious change, progression in the fluid types during that period, and the Williams suite would be in place during that later period when the steep structures are more prominent, and we certainly see a strong association between the Cloncurry fault and a significant gravity anomaly that's interpreted to be associated with that Williams suite. Now, there's a lot more work to do and thinking to do, and to put the deposits into that context, because we've got looking at Osborne, Pegmont, Cannington, they're different ages, different deposit types, but we can start to pull together that evolution with the integration of the seismic and the MT and eventually some joint inversion with the gravity data to better understand the geometry and the evolution. So I just want to very quickly show you a comparison of M6 and CF3 because they're 100 kilometers apart, and both the seismic structure that we see and the MT data is remarkably similar. So this MT data looks a bit different to what Janelle showed you because this is the 2D inversion. But we see these same east dipping conductive anomalies at the same level, the moderate conductive zone in the top of the numal. That gives us a lot more confidence about the continuity of some of those major structures through this area. And we can use that to build in our geological model. So I don't want to go through all these conclusions in detail, but the one thought I really want to leave you with is that the crustal architecture and extensional fault system were there by 1620, and they created a fundamental framework that controlled later deformation, has implications for broken hill style mineralization, as well as other deposit types. So thank you very much. And I know this was a bit rushed because it's built on a couple of years of work and a couple of studies, but I've included at the end details on a lot of those earlier talks and reports. So, so you'll have that if you want to look at anything in any more detail. Thank you.
Thanks so much, Karen. Are there any questions for Karen? Dave's going to run around with the microphone.
Hi, Karen. Can you hear all right?
Yes.
Yep. Yeah. Thanks. It was a great talk. I'm just wondering how your interpretation affects models for how Mount Isa links to stuff further to the east in terms of sort of exotic terrains and tectonic sutures. In connection to Georgetown and
yes. Okay. So
context.
So this image sort of shows it. So I didn't really touch on that. So I don't think, because there has been the suggestion that that Eastern numal represents Laurentia, and I struggle with that. In part because of the similarity and continuity of the Soldiers Cap group and Etheridge groups. Same age, same package, they have those same iron tholiites. And the suggestion that I made that this Eastern numal terrain is the one that continues south and that we're seeing on CF3 and M6 also doesn't support that. Obviously, there's more work to be done to assess that, but I would still see Laurentia as being further east.
There's another question.
Hi, Karen. It's Dave Purdy here. Yeah, amazing work. Really great to see that. Question I had is about the neodymium model age step that you see. I think you mentioned that it was related to the presence of the numal terrain and rocks being sourced from that.
Yes.
But it doesn't seem to correlate, like on that figure there, it's sort of further to the west.
Yes, so it's so the guts of the Williams suite. Okay, so in short, I agree with you. So the guts of the Williams suite is here in the east. We have one or two intrusions that go as far west as the Pilgrim Fault there, just north of, in the Bidakudi area. It's interesting. I think we need some more data and hopefully some more of the younger intrusions in the west with neodymium constraints to better assess that. So we can still have things. Well, I guess I'm not a magmatic specialist. So the question is, can we still have things being sourced a bit deeper or traveling from this source area to the east? And that's something I'm really arm waving here. But I've been consistently pondering how strongly this age is associated with just the Williams suite. And if we really need to get some neodymium model ages on older and younger granites in that area, which are few and far between, to better understand it. Because there is the option that Dave Champion's always flagged that it may be similar crust, but it is reworked with the introduction of some juvenile material.
Thanks.